the analysis is different. Okay, so for thick wall, this is fine. Okay, I sincerely apologize for this. Okay, wasting your time, but you just see how we do troubleshooting. Okay, trying to have checkpoint to know where we gone wrong. That is the critical part. Okay, thank you for you guys for helping me. Also, I'm ever so grateful for your patience. Okay, right. So this is the shearing stress at point A. Then the next one that I'm going to do, I'll tell you one thing for sure, my confidence has been affected. Okay, so the next thing that we're going to do is we're going to find, okay, we're going to find the shearing stress at point B. Okay, we're going to find the shearing stress at point B. Right. Okay, I'm going to, that's where things get really interesting now. So this is our neutral axis. The shearing force is coming from the vertical again. Now, can someone tell me, right? How are we going to find the shearing stress at point B, please? Can someone just try to? So I'll give you I'll try to help. You guys have to answer me, okay? Are we going to consider the start point from alpha, or are we going to consider the start point from beta?
From beta?
From beta. Well done. Why? You are absolutely right. Why?
Because calculating it from the top is more complicated than the bottom?
No,
remember
no.
something about that. From the bottom is the max, your Y max technically?
No, because you can't cross the centroid.
Yeah, the rule says what, right? That's where this topic is so confusing, right? For mechanical engineers. Rules, okay? If we were to start from the top, okay, I'm going to draw this. We're going to start from the top, okay? Oh, I'm so happy that you guys are. I love it. If we were to start from the top, right? So if this is our, sure. Hey, learn now, okay? It's okay to make mistake. I want you to make mistake, and we learn now, okay? More important than you learn during your final exam, then you don't. If we start from the top, we have to take the first moment of area, right? At point B, you have to take this region, yes or no? Right? What is the problem with that? Anyone?
It passes through the centroid.
Yeah. What is the rules that we have stated? So the rules, I'm going to copy these rules again. Okay. All right. So one of the rules, right, that we have derived is what? Right? The rule number 4, first moment of area cannot cross or intersect the what? The centroid. Right? So I had this problem also. I had this problem when I was an undergrad. Even I have this problem when I'm teaching this topic. Okay, that's why I have to write down these rules. Okay, so when we want to go to B, we analyze from the top down or alpha down. Why we do that? Because as mechanical engineers, we have to see. Seeing is believing. The first thing that captures our mind is Eugene. Vy is coming down from the top. That's why we have to go from the top to the what? Bottom. Am I right? That's me. Okay, if I think like that, most of you are brighter than me. You will think the same. But no, the problem is when that's the case, the first moment of area cross the what? Cross the neutral axis. So for this case, our analysis has to go from where? Where I'm writing. So our analysis has to go from this direction. Why that direction? If we do it this direction, what will happen? The first moment of area will not intersect the what? The centroid. Am I right? Right? So if you look at the green shaded region, okay, I'll shade in this color. If you look in this yellow shaded region now, right, it will not cross the what? The centroid. So when that's the case, your analysis, you have to start from the bottom of the web and go towards the what? Go towards your neutral axis. Okay, so we're going to do that now. Okay, so that's where this example, I picked this example for deliberately for this reason. Okay, so we are going to find out the shear xy at point B, right? So the formula still the same, V y over IZZ, right? QZ multiplied by T. Now, for this case, we have to be very careful. Okay, I'll tell you why you have to be careful. Vy still the same. Rule number 1, nothing changed. IZZ still did not change, right? We obey rule number 1. That's why you have to embrace to the rules that has given, right? If not, you'll be confused. Like, okay, I'm going to analyze from the bottom to the top. What is my V now? Should I divide my V by 2 because it's left and right? No. Keep it what? Constant. Okay, keep it constant. I think that's more important than anything else. So so meter times 10 to the power minus 6 meter to 4. Now, can someone tell me what's the thickness? Anyone? What's the thickness that we should be using, please?
30.
30. No, 30 is the, not this 30, right? 30 is from the edge to the web. So the thickness of the web is what? Anyone else, please? Or same person, I don't mind. Yep.
0.02, but you have to multiply it times 2.
Well done. Okay, you have to multiply by what? 2. The reason why you have to multiply by 2, because we have what? Left and right web. Okay, a lot of times students make a common mistake by not multiplying by 2. So next comes to our QZ, right? So it's still A y bar. So the area, the width is equal to 0.02. The depth is 0.03, right? And then the 65. So now getting your information right is important, okay? Or organizing your information properly is critical. So we know the distance from here to here is 65 millimeters. Okay, and because this is 30, the individual centroid is 15 millimeters, right? Why 15? Because 30 divided by 2. So we know that AY will be equal to 65 or 0.065 minus by 0.015. Okay, minus by 0.015. So over here, you will have 0.065. Help me check, okay? I might make mistake again like before. Again, one mistake I make, you get a pint of beer. And then you have to multiply by 2. Why we have to multiply by 2 is because, again, it's your what? Left and right web. Okay, so let me 0.065 minus 0.015 times 2 times by 0.03 times by 0.02. I get 60 times 10 to the power minus 6. Yeah, so let me do it again. 0.065 minus by 0.015 times 2 times by 0.03 times by 0.02 is equal to 60 times 10 to the power minus 6. This is meter cube. Okay, so from here, your shear xy at point B will be, so the Vy is again 90 times 10 to the power 3, 60 times 10 to the power minus 6, divide by your IZZ, 5.8133 times 10 to the power minus 6, and then the thickness will be 0.02 and then twice again because of left and right. Times by 60 power minus 6 divided by 5.8133 power minus 6 divided by 0.02 divided by 2. So it's equal to 23.222, right? Times 10 to power 6 Pascal. Okay, right. So I'm going to do the same again. Okay, if anything goes wrong, is the distribution. Okay, so I'm going to use the same equation. I'll tell you now, I'm so nervous. Okay, I'm so nervous now. Right, so this is the function again. Right, this is the function again that we're going to use. Okay, so that's the function. Right, so if we're going to use the function, the shear xy at point B, right, when y will be equal to, so y will be equal to, so from here to here, right? So from the top is 30, so this is 35 millimeters now, right? Because the datum starts from the neutral axis, but the analysis starts from y max and it goes to the what? It goes to the neutral axis. So if I put that expression in there, you guys can't see it. My pen is shaking, okay? So 32.705 times 10 to the power minus 6. We know this expression is correct already. Okay, we are very, very sure. 7.7409 times 10 to the power 9 powered by or multiplied by 0.035 squared. So this will be equal to 32.705 or power positive 6, to apologize, not negative. This is positive, okay? So 7.7409 power 9 multiplied by 0.035 squared. Okay, so it's 32.705 power 6 minus by, so I get 23.222. Whoo! Relief. Okay. All right. So if we go back, yeah, that's it. Anyone, any questions so far? Anyone, please. Right. So to summarize, when you have a structure like that, like this at the web, especially at the web, you have to consider the first moment of area for QZ. You have to multiply by 2 because of your what? Because of your left and right web, and the thickness you also have to multiply by what? 2. Okay. If you miss up on this, and that's where trouble comes. Okay. So that's where we are going to have issues, right? Anyone else? Any questions, please? Anyone? No? Okay. So the next thing that we will go is a new topic. Here's a new subtopic. So we're going to look at longitudinal shear. On a beam section. Okay, we're going to look at longitudinal shear of a beam section. So we're going to analyze. So for this case, what is so different? Okay, what is so different? Okay, so the difference is this. We're going to analyze the strength of the joints in shear loading configuration. Okay. So the most important thing now is joints. Okay, we're going to look at joints. And the joints, for this case, the joints the joints can either be